Hello, this video is covering some of the regression tools you're going to need to make equations and understand residuals and looking at the conditions you need to make sure the data set that you have in front of you is good for a linear model. So you can see the first slide here talks about the equation here. You see how we have y hat for the least squares regression line, and then b0 represents the y-intercept and b1 represents the slope. We always use that same notation. You have to have a hat on top of your y variable in order to let the reader know that this came from a sample and you're trying to use it to make predictions for a population. So it's a predictive kind of indicator. Right, the estimate, right? They use the word estimate there, predicted value. Conditions. Now, if you want to look at a set of data like it's been graphed out and say that this is good for a linear model, there's a few things you got to check. First of all, you need to make sure it's quantitative data, not categorical, which is a lot of times you don't even have to check that, because if it wasn't quantitative in the first place, you wouldn't be able to graph it out. So sometimes that's kind of checked, but it's not a big one. You can kind of ignore that a little bit. Straight enough condition, you do have to check to say, yeah, that looks straight. Now we do this two ways. You just look at the scatter plot, or you also look at the residual plot. And I'm going to do that in just a minute. No outliers and no fanning. So these are the conditions that you need to kind of say, yeah, I can use this linear equation to make predictions and to look at my data sets. Okay, so then the last thing is just really understanding what a residual is. Like, what is a residual? Well, it's the difference between the actual value you got from one of those data points in your sample versus what this linear equation, the least squares regression line, is predicting. So there's a difference between those, and I'll show you that as well in just a second. So, sorry. So if you remember, like, I'm going to start off with kind of R and stuff, because we need the correlation coefficient in order to calculate the equation of a line, to find the slope and to find the y-intercept. And it starts with correlation coefficient. So there's another video all about this, so I'm not going to get into details, but just remind yourself that the correlation coefficient comes from the z-scores of the x and y, that you are making rectangle areas for each data point from the residuals. And the more positive you have a positive correlation, which goes right along with slope. You'll have a positive slope. The more negative areas you have, our data points in this quadrant and this quadrant down here, then you're going to have a negative R value and also a negative slope. So the R value and the slope go hand in hand. They're calculated together. So that's why I brought that up. Let me get this down out of the way a little bit. Okay, so you can see here the equation for how to calculate R. That, like I said, that's in a different video, so check that out later. But what we need now is to find out how to come up with our slope and then our y-intercept from the information that we have. Sorry, this is kind of hidden a little bit, which I don't like. Can I grab this? Oh yeah, good. Sorry. So you can see that equation down there. Okay, so the slope comes from the R value, the correlation coefficient, and also the standard deviation in the y direction of just your y list, and the standard deviation in the x direction of your x list. Okay, so those are the three things you need, and you can get those from a one variable stat or a computer printout maybe or something. But you need these three numbers, and usually they're given to you as statistics before they ask you to calculate the slope by yourself or by hand. Once you get your slope, then you can just use the equation of a line to come up with your y-intercept. This is just a rearranged version of the equation of a line. But one special case or one special thing has been changed. So besides the slope that I now have figured out, I'm going to add in the fact that the center of my x direction and the center of my y direction will always be on my least squares regression line. Why? Well, because this fact, the center of this where the slope is calculated and where the R is calculated, the center of this is exactly where the mean in the X direction and the mean in the Y direction is located. So what's going to have a z-score of 0? Well, the mean is. What's going to have a z-score of 0? Well, the mean is. So the least squares regression line will always go right through where the z-scores are 0, but that also happens to be exactly where your X list of numbers, where the mean is, and the mean of the Y values as well. So this is like one data point, and pretty much the only data point we know for sure is going to be on my least squares regression line from my sample set, right? It's not even really a point. It's kind of just the means, right? So the means will be on that regression line, not necessarily a data point. Okay, so I'll put those values in along with my slope, and I can get my y-intercept. And we will have an example of that in just a minute. Right here. Let me go back though, before we do that problem, let me go to my TI Inspire, and let's look at an example of a problem. This is the data we've looked at before with the roller coaster drop in feet, and then the speed of the roller coaster in miles per hour. So we've kind of used this a couple times now in a couple videos, but I use this to explain regression and stuff as well. Okay, so the first thing though is let's just look at this. You can use, I'd put my points in there, and I would check to make sure that a linear model is a good idea. But even though I might look at it and say, yeah, that looks pretty straight, what I want to do is go ahead and put my regression on there, which I've already done, but I'll just show you where to do it. So you do it right here, go into regression, and you show your regression. So once you do that, you'll get this line to come up, and the R square should be underneath it and all that. But remember, R and R squared is not an indicator of how straight your data is. So you shouldn't look at the R to tell you whether a line is a good model or not. You shouldn't. You should just be looking at the pattern. Okay, so even though I put the line on here, I still haven't determined if a line is a good model yet or not. The next thing you need to do is go to your residuals and show residual plot. And that will come up down below. And I'm just looking for any kind of pattern in there. Or I'm looking to see if it's nice and evenly distributed about that line down there. So this looks pretty even. I got one below, one above, a few below. There's some below, some above, and it's all nice and evenly distributed. I don't see some curve in the pattern, right? Some curve in the pattern, anything like that. If you see anything like that going on, whoops. If you see anything where this is going like this, and you have data points, whoa, undo. Didn't want to do that. And I lost my thing coming up. That's fine. If you see a pattern in the residuals at all, then you know you don't have linear data anymore. I lost my my screen, but you don't need to see me anyway. That's okay. You can just hear my voice. Okay, so moving on. So now I've determined that this is a linear, or that a line is a good model, right? So a least squares regression line is a good model. It fits. I don't see any real fanning going on. There's a little bit of fanning on the left, but not enough. Like that's where this points and these points are coming from, but not enough to make me change my mind about whether it's a line is a good fit or not. So, and I don't really see any outliers or anything either. So residuals look good. There's no pattern. There's not enough fanning to cause me concern, and I don't see any outliers that are going to cause me concern either. Okay, so that's what you're really looking for, and that's how you determine if a line's a good fit. Once you do that, then you can go ahead and use your equation to make predictions and things like that. Okay, so let's practice this finding the equation of a line using my statistics. Remember all this, like I can find an equation of a line, I can put in an equation of a line, but until I really check the shape of it, you can't really say a line is a good model or not. So just remember that when you're doing a lot of stuff like this. It doesn't help you determine if it's a good model or not. That's a different thing. Okay, so how do I do this? Well, I want you to stop the video, pause it, and try it on your own. And then like using the tools that we showed here, these two things at the bottom. And when you're done, start the video again, and I will start the answer slide so you can see the answers. Okay, you're back. Here we go. Here are the answers. So you should have used the R value, the coefficient of correlation coefficient in here, and then times the SY over SX. So the standard deviation of the Y divided by standard deviation X, and that will get your slope. You take that slope and you put it back into the equation of the line. And you have to add in your mean of your X and the mean of your Y. So here's the mean of the Y and the mean of the X. Solve that and you get 105.9 for your y-intercept. So I have my slope, I have my y-intercept, I have enough to write the equation of a line. I didn't actually write it out, but you should, right? Okay, so then same thing here. You can see I took my R and my SY and my SX, got my slope, and then went ahead and used that slope along with the mean of my X's and mean of my Y's and got my y-intercept. Okay, moving on. So coefficient of determination, this is an equation of how this is found. It's pretty rare that you would have to do anything like this by hand, but this is really where it comes from. The SY is the standard deviation in the Y direction, and the SE is the standard deviation of the residuals. The reason this is here is not because you have to calculate R by hand using this method. You would use the other method that we did. And if you wanted R squared, you would just use the old method, the easier method, and get your R and then square it to get your R squared. Like you would never really need to do this. The reason this is here is because it's a good visual of what R squared means, what it represents. So let's decompose it a little bit. The standard deviation in the Y direction, right? I got a little picture here for you. This is a graph of the miles per hour, but without the height of the drop on there. It's just the miles per hour. So this is all the Y values just by themselves. You have to realize that this has quite a bit of spread, right? The standard deviation of this might be like from 65 to maybe 75, like 10. So that might be a standard deviation of about 10, right? So this bottom number would be like 10 squared. Okay, so you get like 100 on the bottom. The top is telling you, well, after you put on the, and I'm going to show you that right here. So after I put on my drop, right, you see how it changes. Now I'm talking about this. Let me get rid of the residuals. We don't need, well, let's look at the residuals. Because what it's doing is saying, I'm going to take all these residuals, which if you notice, actually I am going to get rid of the residuals because I want you to see this. Hide residuals. It's taking all those residuals and squaring them up. So I'm going to say show residual squares here. It's taking all these areas. So it's taking the height from the predicted value on the line of best fit, or the least squares regression line, and taking that distance to the actual point, which some of them are big, that's a big residual, and some of them are small. This is a little teeny residual down here. I think I can write in there, right? I'm going to zoom in on that. This is a little teeny residual, right? So when you square that, you get these little, like big squares and little squares. But when you add all that up, it's going to be a lot less than if I were to take 10 squared over and over and over again for all these, right? Like the average of these, there's some big ones, but there's a lot of little ones and a lot of medium-sized ones. So the average square, like the average area of one of those squares, is going to be less than 10. It's going to be less than 10. Like there's just no way it's going to be more than the 10 squared, which came out to be 100 for us, right? So when I look at this equation, I had a standard deviation without the drop on it of about 10. I squared it to 100. My standard deviation for, like, I don't know, what's kind of an average square? Let me take a kind of a, whoops, let me zoom out on that. You know, what's an average square? Like maybe one of the, maybe this one right here or something. or maybe something kind of this size. That's so small. Like this little bit here is so much smaller, as an average. Even if it's this big, that's still a lot smaller. That might be 5 or something, right? Maybe 2 or 3 or 4, maybe even 5. I doubt it'd be 5, but maybe. So you're getting 10 squared on the bottom. You're getting something like 5 squared on top. So 25 out of 100 is 25%. So we would say that 25% is being is 25% of my variation. Like, remember I did, let me, can I remove my x-axis? Remove x. So I started with this much variation. After I put the drop on there, there's 25% of my variation left over. That's how much variation I still have. So what percentage of the variation I started with did I end with? Well, 25%. So in order to get the coefficient of determination, I would subtract that from 1 to ask myself how much variation was removed. So 25% is left over. That means that 75% of it was removed just by the act of putting on the drop feet onto that set of miles per hour and trying to correlate those. So that's why the coefficient of determination is worded the way it is. It's saying that, okay, it's 75% of the variation I used to have has been removed. And because of this association, and 25% is left over and is due to other types of variables and other types of association. Okay, so that's the reason this is here, is to kind of get you to understand like how residuals really play a big part in these R squared and understanding how good of a fit things are. Okay, last thing I'm going to just, I already talked about that. So that's pretty much it. The standard error equation is here. This is really just the standard deviation of the residuals. So notice how it has n minus 2 on the bottom though, not n minus 1. Because you have bivariate data now, we're going to introduce a little more error. So it's really close to the same idea as the standard deviation, but it's for residuals. So you're just taking all your residuals, squaring them, adding them up, divide by n minus 2, and then take the square root, just like you would with standard deviation. Very similar formula. But okay, that's enough for now. You've learned how to get the equation using statistics. You've learned how to check to double check to make sure that a linear model is a good idea and a good model. And you kind of learned a little bit about residuals and R squared and how those come into play.